that they were very limited and had to spend it on something. All right, so listen up. What we got today is the next section of this chapter 6 in sapling. Hopefully we don't. I mean, I want to go to online only because I would rather just not be here in the morning.
You do want to go online?
Yeah. But it's not my choice. I don't get any say in the matter.
If we did go online, could I Skype you to get help?
You can email me. I don't know that I do Skype. I mean, if enough people were asking for help, I might do Skype. I'd probably just do emails and then post little videos on Google Classroom because if you're asking a question, somebody else is probably gonna have the same question. So I'd make a little YouTube video and post it on Google Classroom. But hopefully we don't actually go that quickly because we're getting closer and closer and closer to stoichiometry. And if y'all have to learn stoichiometry at home, it's going to be pretty difficult. So we'll see how this goes. Today we're going over electron dot formulas, which we've already talked about electron dot structures or the Lewis dot diagrams. It's basically where we do the little dots around the element symbol to tell us how many valence electrons they have, how many electrons are in the outermost shell. And looking at your periodic table, remember that this stuff does not work for the pink block, and actually it's right on the front. Is it the front or the second page? I think it's the front page of your worksheet. You got the little periodic table diagram there with the pink part cut out. And so the first two columns, you have one dot on everything in that far left column, and then it goes 2 dots, 3 dots for the one that starts with boron up top, 4 dots for carbon, 5 dots for nitrogen, 6 for oxygen, 7 for fluorine, and 8 for everything in that right column. So you can look really quickly at the front of that piece of paper and find out how many dots any of these elements have very, very quickly. So today we're going to go through ionic bonding and covalent bonding. I already said that the dots represent valence electrons, and valence electrons establish an element's chemical properties. So what can that element do? What kind of combinations can it make? What are the new chemicals going to be like? That depends on the valence electrons. So if we count the valence electrons and we look at how they combine, we can predict what the chemicals will look like, what the molecules will look like, and what kind of things they'll do. So this is what I was referring to on your sheet. It has everything 1 dot, 2, 3, 4, 5, 6, 7, 8. So notice everything in a column has the same number of dots. Everything in this column has 8 dots except for helium. It has a max of 2. Everything in this column has 4 dots. So every single column has the same number of dots in it. So you can look at this really, really quickly and figure out how many dots an element should have. So use the octet rule when drawing electron structures for compounds. Almost everything wants to get up to 8. 8 is the total max for almost everything. The only two that don't get up to 8 are hydrogen and helium. In that very first row, hydrogen and helium can only hold up to 2. So if the octet rule for everything, neon already has 8. It's not really going to combine with anything else. It doesn't want to get rid of any electrons. It doesn't need any more. Neon's what we call inert. It's not going to react with anything else. It can bump into all the other elements and not do anything. For hydrogen and helium, they're after that duet rule. They want to get 2 electrons in the outer shell, and then they'll be nice and happy. So for ionic bonds, remember the difference between ionic bonds and covalent bonds last week. Ionic bonds, an electron transfers to the other atom. So for example, they'll probably do another example in a second, but calcium and chlorine, how many dots does calcium have?
2.
It has 2. Let me pick a better element. It does have 2, which is fine, but I don't want to get too complex right now. Sodium, that's what I meant to do. Sodium has what? 1. Nice. So sodium has 1. Chlorine has how many? 7. 1, 2, 3, 4. And remember this. Space them out first. Go clockwise when you do your dots, and then start to double them up. And the reason behind this is you don't want to have too many doubled up. You want to have as many single electrons as you can. So once I get 4 in, now I can start doubling them up. 5, 6, 7. And so I have one available spot here for chlorine. The sodium only has one. Metals want to get rid of their electrons and become positive. Non-metals want to take in electrons and become negative. So to write an ionic bond with the Lewis dot structures, you're going to show that transfer. You're going to actually have the electron from sodium leave the sodium and go over to the chlorine, and that's how you're going to draw it out. So here, is this actually a little video? Yeah, watch. The electron from the sodium, this is like awesome graphics here. Yo, it's very impressive. Somebody spent like a whole day working on this probably. An electron left the sodium, went over to the chlorine. Now the chlorine has how many electrons? 8, and it has one extra electron, so what's its charge? -1. It's got that one extra electron. The sodium lost an electron, so now it has one less electron. It's going to be a plus charge. So when you see covalent bonds, ionic bonds with the Lewis dot structure, one of the atoms will have all the electrons, the other atom will have none of the electrons, and you'll see the positive and negative charges there written out. And so if I just show you this, you should be able to see, oh, sodium should have 1 electron. It doesn't have any. Chlorine should have 7. It has 8. That means an electron actually transferred over. Electron transfer is ionic bonds. I also have the charges, which tell me it's an ionic bond. This is an ionic bond. For covalent bonds, we'll do something very different. So that's one of the ways you can kind of tell it's an ionic bond. Another way, you have a metal and a nonmetal. If it's a metal and a nonmetal, it's ionic. If it's 2 nonmetals, it's covalent. And then if it's 2 metals, we'll get to those later in the week, that's metallic. So ionic bonding, to draw the electron dot structure for the compound, draw it for the ions in the compound next to each other. The ion dot structure show the valence electrons and the charge. You're going to have the electron already transferred. So potassium should only have 1. Bromine should only have 7. But you actually see that's different here. Potassium doesn't have any of them. Bromine has all 8. We have the plus and the minus. That's how we're going to draw an ionic bond with the Lewis dot structures. Now, covalent is different. Covalent, you're actually sharing electrons in between the atoms. And I showed you a little bit of that before. They talk about the charge difference or the electronegativity difference. If the difference is less than 1.7, they're generally considered covalent. So if you have a small difference between your numbers, they're going to be a covalent bond, and they're going to have to share electrons. So there's a couple of problems on sapling where you have to do a little bit of like plus minus math just to figure out if is my difference 1.7. If it's over 1.7, it's going to be ionic. If it's under 1.7, it'll be covalent. So covalent bonds are formed when 2 nonmetallic. Remember, you can also look at the elements. If it's 2 nonmetals, they're going to share electrons, and you're not going to have an electron transfer. We have 2 different types of covalent bonds, nonpolar and polar. Nonpolar is where they share the electron equally. It's usually going to be between the same types of atoms, like 2 bromines can share electrons in between them. Neither one of the bromines is going to be stronger than the other one, so the electrons are going to sit pretty much in the middle. Polar covalent bonds are where you have an atom that has a stronger attraction for electrons. It's going to hog the electrons most of the time. They're sharing, but they're sharing like your friend shares their video games when you go over to their house to play video games. Most of the time, they're the one playing it. If it's not a like multiplayer game, but it's shared equally in nonpolar ones and not shared equally in polar ones, and we'll see examples of that. So to determine polar and nonpolar, consider the electronegatives. You can look them up on the chart, or just kind of look at how many electrons the atoms have. How many does each of these have? 1. So if they share them in between them, is any one of them going to be stronger than the other one? No. Both the hydrogens are going to pull the electrons equally. If they share these electrons in between them, now how many electrons does each of the hydrogens have? 2, which is the most that hydrogen can have, so they're both satisfied. When we draw bonds in Lewis dot structures, you draw a solid line in between them, and a solid line is equal to 2 electrons There's one from each atom there. Atoms with very different electron negativities form polar covalent bonds. So the example here is the chlorine and the hydrogen. They're going to share an electron here because hydrogen is going to act as a nonmetal. So you're actually going to form a bond. But the chlorine is obviously much better at stealing electrons. That's what chlorine does. And so while they're sharing these, the electrons most of the time are going to be over here at chlorine's house. They're not going to be hanging out with the hydrogen all too much. And so that's a polar one. The chlorine's going to be more negative. The hydrogen's going to be more positive. But technically, they are sharing electrons in between them, and it's a covalent bond. We also see that with water. So when we draw the electron dot structures for covalent compounds, evaluate the dot structures for individual atoms, determine how many times each atom can bond. And this is the point here. We have bonding electrons and non-bonding electrons. So for example, let's do what they just did, hydrogen and chlorine. Chlorine has how many? 7. So what we're going to call these electrons that are already paired up, those are non-bonding pairs. And it's easy to remember because it's right in the name. Bonding electrons, does it have the word pair with it? No. Non-bonding has the word pair right in the name. And so what's a pair of anything? 2 of them. So if I have 2 electrons right next to each other, that is a non-bonding pair. And if they're a non-bonding pair, what can they not do? Bond. They can't bond. So I can't hook up any other atoms to these 3 sides. The only one I can hook up another atom to is right here, which is called what?
Bonding electron.
The bonding electron. It's by itself. It doesn't have a pair. And so it's looking for that extra electron to kind of be together with it. Hydrogen also has one of those. And so when I combine the hydrogen and the chlorine, I form a bond in between those. Now this hydrogen has how many electrons? 2. And the chlorine has 1, 2, 3, 4, 5, 6, 7, 8. And so now both of them are satisfied because hydrogen has 2 electrons, which is the max. Chlorine has 8, which is the max. And we've kind of hooked that together using our bonding electrons versus non-bonding pairs. So you will see questions on the test. I don't know if they'll be on sapling. That ask you about non-bonding pairs and bonding electrons and how many you have. I think you got a couple on sapling that ask you that. So their example here, bromine. I have 2 bromines. How many electrons does bromine have? It's not up there, but how many does it have? 7. So each of those with 7 electrons for bromine is going to have a non-bonding, or they're going to have 1 bonding electron. So 1, 2, 3, 4, 5, 6, 7. So I have this bonding electron over here, and if I have 2 of them, I have 2 bonding electrons, and so those are going to sit in the middle and form my bond between my 2 bromines. And so that's what's forming that bond there. Is each of them have 1 bonding electron that they bring to the table. If I have a couple extra things, well, they give you the steps here. I'll show you double and triple bonds in a second. Step 1, draw the dot structure for the atom. If you can imagine this and get through the questions, that's fine. Like, I'm not going to check your work on drawing, but I would just get used to drawing it or looking at the study sheet to figure out how many electrons you have, because you need to know how many non-bonding pairs you have and how many bonding electrons. That lets you know how many you need to bond. Draw the dot structures for the surrounding atoms and make sure that when the bonding electrons are shared, all of the atoms in the compound have an octet or a duet, depending on what they want. So you want all the bonding electrons used, and you want every atom to either have 8 or 2 electrons, depending on what the atom is. So draw the Lewis dot structure for nitrogen trihydride. How many nitrogens am I going to have?
1.
Just 1. How many hydrogens am I going to have? 3. So NH3, this is ammonia. That's what I'm trying to do here. So before I let them do it, how many dots does nitrogen have? 5. That's 5, right. So I have my nitrogen. 1, 2, 3, 4, 5. How many bonding electrons do I have here?
3.
3. How many hydrogens do I need to hook up to this?
3.
3. So it makes sense that I'm going to put the hydrogens on the sides that have bonding electrons and not up top, because there's a non-bonding pair there. I can't hook that hydrogen up right there. So I'm going to have a hydrogen over here, a hydrogen over here, and a hydrogen over here. Each one of these has an electron, which I just put facing the other atom, so it's easy to hook them up. And then I'm going to draw my bond in between. And so now if you look at it, each hydrogen has how many electrons?
2.
2. And how many does the nitrogen have? 1, 2, 3, 4, 5, 6, 7, 8. So the nitrogen should have 8. And there's no extra electrons hanging out just by themselves. They're either in a non-bonding pair or they're tied up in a bond. So everything's nice and neat and works out like we want it to. That's what you're looking for when you build these kind of structures. So same thing, nitrogen is 5. I put the hydrogens around each of the bonding electrons. I draw my bonds and make sure that all of the electrons are used up. And so everything's good here. Multiple bonds, if you have extra electrons left over, you're going to have to make a multiple bond out of this. So oxygen has how many electrons? Valence electrons.
7.
Oxygen has 6. So I have an oxygen here. 1, 2, 3, 4, 5. And I'll put this one over here. 6. An oxygen over here. 1, 2, 3, 4, 5, 6. Now, I'm going to make this bond, right? But what's the problem here? First off, huh?
Oh, you got not clockwise.
Yeah, I got 2. Well, the clockwise, you want to do it by itself, but if you got to hook them up to other atoms, you can kind of fudge the clockwise thing a little bit to make it kind of make sense spatially. I have 2 bonding electrons that aren't bonded. That's a problem. And also, each oxygen only has 7 and not 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So my oxygens don't have 8, and I have 2 atoms or 2 electrons that aren't bonded. What I need to do is make a double bond here. So I'm going to move this up. I'm going to move both of those up, and they're going to form this second double bond. And now that they've done that, I have 1, 2, 3, 4, 5, 6, 7, 8. Well, no, sorry, I counted that wrong. My bad. 1, 2, 3, 4, 5, 6, 7, 8 for the left one. 1, 2, 3, 4, 5, 6, 7, 8 for the right one. And every single electron is bonded, and both atoms have 8 electrons. So that's what I'm looking for. Oxygen will have a double bond. Nitrogen has 3 bonding electrons each. If you're bonding 2 nitrogens together, it's going to need a triple bond. I think triple bond is the most you can have. I don't know that anything has a quadruple bond, but the more bonds you have, the harder it's going to be to break those bonds if you're trying to do a chemical reaction or something. So that's the end of the PowerPoint. The assignment is open and assigned. And if you have any questions, please let me know, and I will be around to help you out. For the online people, please send me an email, and I will email you back. Have a nice day.